and then spend a little time talking about your upcoming test. So I activated the test today, which means it should show up when you hit syllabus on the Canvas shell, and it will be accessible after midnight tonight. Not that I really expect anybody to log on after, like at 1 o'clock in the morning, to take the test, but it will go live at that point. So then you have 4 days. You have Friday, Saturday, Sunday, Monday, and it will shut down at 1 minute before midnight on Monday. Okay, this doesn't mean you can work on it continuously for 4 days. Once you start the test, the way the Canvas system works is it starts a timer system. So once you begin the test, you have 4 hours before it shuts you out. And you can't stop, you can't pause it, okay? It just, like, it starts the timer, you have 4 hours, that's it. So kind of keep that in mind when you are logging in to take the test, that you need to hopefully make sure that you have as best an internet connection as you can get, and that hopefully people won't be bugging you, interrupting you, if possible, for the time period that you are intending on devoting to the test. You can use your notes, you can use your textbook, your lab book, your homework. Because it's on a lockdown browser, you can't go surfing for stuff. Don't use each other. Okay. The way the test is designed has a mix of questions on it. So there's a few true false. There's a goodly handful of multiple choice. There's, I think, 2 that involve matching. There's some short answer, meaning a couple words, or meaning here's a picture, answer the question that is related to the picture. And there's obviously some math involved, because especially chapter 1 has a certain amount of math involved in it. So let me kind of run down through some of the basic topics so that you can just kind of have an idea on what you need to think about in terms of things you need to be capable of doing for the test. So let me kick on my whiteboard here. All right. So this is just kind of, it's not necessarily an all-inclusive list, but it's the things that we covered, and definitely things that you should be aware of in terms of being able to have the knowledge or be able to do the calculations. So one of the things we did close to the beginning of the chapter was scientific method stuff, which then also involves quantitative and qualitative difference in observations. Think about your homework set. Okay, you did homework set for chapter 1. One of the questions involved being able to differentiate between qualitative versus quantitative. All right, so we did some solid, liquid, gas, basic theory, some states of matter, what makes them different, what things they have in common, that kind of thing. And then we moved onward to talk about a little bit about homogeneous versus heterogeneous. Basically, if we're talking about mixtures, I think everybody's done lab, except, I was going to say, unless by some chance you have lab later tonight with Mr. Siniak. I think everybody else has done the separation of mixture lab. So that particular mixture was relatively homogeneous, okay? When you took it out of the beaker to put it in the evaporating dish and took it to the hood to cook it, when you kind of look at it, it's relatively the same all the way through. So kind of keep that in mind as you're thinking about that particular topic. We also did properties. We did both physical ones and we did chemical ones. So make sure you have some clue on what the differences there are. Along with that, we did changes. Again, this kind of falls in those two different categories of the physical ones versus the chemical ones. We did reaction observations, things you see that indicate a reaction is taking place. And then we moved on into units, keeping in mind that you should definitely know the base SI units, things like meter and kilogram and second, etc. But you also need to be able to do scientific notation. Okay, again, this kind of goes back to homework topics. You also need to be able to do conversions between metrics, okay, but also conversions between other units. If I give you data such as 2.54 centimeters per inch, if I gave you inches, you should be able to convert a number over to centimeters. So both metric ones and other ones. Keeping in mind that all of this also ties into the idea, and this is again kind of a lab versus lecture idea of accuracy versus precision. Make sure you know what the difference is. And sig figs. One of the things that you need to keep in the forefront of your mind when you are doing significant figure problems is that there are two phases to this idea. There is the phase of doing math, but there is also the phase of doing the rounding as needed for your calculation. I'm actually staring here looking for my calculator. Hang on a second. All right, how about an example? If we had 54.1, and we're going to multiply it by 99302. Okay, so if I want to do this according to sig fig rules, so first step is your calculator step. So 54.1 times 99302. Okay, and this is what my calculator gives me. 5372238.2. Okay, so that's my mathematical answer, but it is not my answer in terms of sig figs. My little section here, okay, 54.1, I am only allowed to report 3 sig figs in my answer. If I do it in terms of scientific notation, which might be the easiest way to do it, I would have 5.37 times 10, and I don't have a little upscript thing on this whiteboard. So times 10 to the, and let's see, I need to count my decimal places here. So 1, 2, 3, 4, 5, 6. So times 10 to the 6th. If you didn't write it in scientific notation, you would have to have 537 and then 1, 2, 3, 4 more zeros. Both of those versions of the answer only have 3 sig figs. If you do the math right, but you do the sig figs wrong, the answer is still wrong. Keep that in mind. All right. We also then did a few other multi-step conversions. And my little gadget here is being semi-finicky here. So there is one multiple step dimensional analysis problem. Okay. There's one. Okay. Remember the one from homework that involved the blimp that is traveling and how far does it go and how long does it take? Okay. That one was a multi-step problem. So I have a multi-step dimensional analysis problem that is worth 5 points that is part of this test. You need to show me some math so that if you glitch it in your process, I can potentially give you partial credit if you did some of the initial steps correctly. And then the far end of the chapter, we also did some density and we did some temperature. Again, this kind of harks back to the homework. This is why I design my own homework as opposed to using the digital versions that are sometimes activated for math classes and that sort of thing. Is I design the homework sets to help guide you in the direction of what I think you need to know for the tests. So that is all of the chapter 1 information. So I'm going to hit clear so it will allow me to start all over again. Okay, for chapter 2. All right, so this one has a little bit of basic history in it, but again, you have access to your notes and your textbook, so there's only a couple of questions that involve some basic chemistry history. And then after that, we moved in the direction of how the periodic table is put together. So things like atomic number, atomic mass, subatomic particles, meaning the 3 that we are dealing with in this chapter being the proton, neutron, and electron, which then means you should be able to find out how many particles if you are given an isotope. Again, this is like the homework set. Homework is due tonight. I will post the answer key for the homework sometime tomorrow. That way you can go back and compare your answers to the answer key, see if you're on the right track. But being able to tell how many protons, neutrons, and electrons are part of what you need to be able to do for this chapter. We also did weighted averages as a way to calculate how many or what percentages are contributing to a particular element. We also spent a little time talking about the group. I'll call them numbers and names. Some of the ones that we covered, such things as alkali metals. We also did alkaline earth metals. We're kind of moving from left to right across the periodic table. Transition elements or transition metals might be a somewhat easier thing to do. And I saw somebody flicker in. Hang on. Okay, I'm gonna see if I can. Yeah, because somebody, I get this drop down when somebody tries to log in, and it's like, it didn't let me hit the admit thing fast enough. All right, so transition metals. Okay, the ones at the bottom that are actually called the inner transition metals. Those are all the lanthanide and actinide ones. And then as we're heading over toward the right-hand side of the table, we also talked about halogens and we talked about noble gases. Okay, so those are all categories, and you need to understand how the table is put together. With the final big segment of chapter 2 being nomenclature. Okay, so keep your periodic table handy. You can use the polyatomic table that is in your textbook. I believe it is page 63. I won't swear that's the actual correct number for the textbook. But there is also a polyatomic table in your lab book that is part of the doing of the dry lab 2. And somebody asked me a question regarding dry lab 2 last night in lab, which I will swing around to in just a moment. Questions about topics for this first test?
Yeah, I actually do have a question.
Okay.
I was actually looking at the homework at number 8. I was actually having difficulty trying to figure that one out, where it says like 41 calcium, find how many protons, neutrons, and electrons.
Okay, so let me pick on and I have to figure out where I laid my periodic table. All right, so if I pick on iodine, okay, so I'm going to try to do this using the drawing function so I can show you where the numbers are. So capital I for iodine, okay. On the periodic table, iodine is number 53, okay. But if I choose a different isotope, if I choose isotope 130, okay, so now I want to know how many protons, how many neutrons, how many electrons, okay. So the atomic number, okay, the 53, okay, this bit here, okay, 53, that will tell me 2 out of the 3 pieces of information, okay? So it will tell me that I have 53 protons. It will also tell me, as I try to get this thing to cooperate here, it will also tell me that I have 53 electrons. But in order to do my neutrons, I have to do 130 minus 53. And so I don't glitch this. I'm going to actually use my calculator so that I don't make some stupid math error. All right, so that gives me 77 neutrons. Now, because Microsoft Word does not allow me to print the bottom number, which in this case, when we're looking at this element, is 53, I only included the isotope number. You have to look on your periodic table to figure out what the atomic number is, because Canvas also does not allow me to put a number on the top and a number on the bottom at the same time. So
Okay.
I only included the isotope number.
I see. Okay. Yeah, that's why I was getting some confusion on there. I was like, okay, but now I see what you mean now.
Okay. So you're going to need your periodic table so that you can look up the atomic number. I have provided the isotope number both in the homework set, but also on the couple that are on the test. Okay. Other questions regarding test material?
No, that'll be all for me. It's good. Thank you so much.
Anyone else have questions? Okay, back to the lab thing. Dry Lab 2, which is the nomenclature lab. When you log on to the Canvas shell for lab, there's information in two spots, okay? On the module, there is a Word document that is 6 pages long, okay? You need to download that. You can leave it in digital form if you want. You don't have to print it on paper, but you can. On those 6 pages, there are 120 compounds. The instructions for each portion of that are actually on the page, which is that strip on the left-hand side there for Canvas. Let me see if I can pop this open to make it a little easier to see. All right, let me go back over here to my dashboard. Okay. All right, so when you log in, and you should see something fairly similar. Over here it says pages. And like I said, unfortunately, they're alphabetical as opposed to chronological, which always annoys me. When you click on Dry Lab 2, okay, note, and I have to kind of squish this in order for me to be able to see it. I'll just skip part 2A, okay? There are multiple pages in your lab book. We are not doing part 2A at all. We are doing 2B and 2C, and also not all of either of those. So if I switch back over here to my modules, and I skim down here where it says nomenclature lab report, okay, when you open this, this is where the answer pages are, meaning it is a page for you to put your answers on. It is not an answer key, okay? And take to heart, Google is not your friend, okay? I constantly get wrong answers because I don't know how many people are actually really aware of this. The way Google works as a search engine is based upon popularity. Okay, how many people utilize a given site? As Abraham said, the Civil War ended in 1912. Google is not your friend. Okay, you need to use the rules that were presented in the notes, are also covered in your textbook, are also covered in your lab book. Make sure you are using the rules to do your naming. And there are tips here in the module to give you some guidance as to what you should be focusing on for each chunk of the lab. So they're on the first page. They're all molecules at the top of the page that have only 2 elements. When you get to the middle of the page, if you read the lab book, it kind of implies that you are supposed to do stock system and older system. I am only looking for the stock system. At the bottom of that page, there are 4 molecules that are all acids. You must name them as acids. As you proceed onward, you will see that the ones in number 4 have no metals, which means you are focusing on the prefix system. And then the rest of that page is predominantly various combinations. If you're comparing this to your lab book, you will see that I did not assign any from number 7 or number 8. I then skip over to part 2C, and again, skipped one of the problems entirely. I skipped number 1. 2 allows you, or focuses on using Roman numerals. There are some hydrates in just a couple in the number 3 set. So make sure you read the little segment in the lab book about the hydrates. Number 4 is again back to acids, but it's more than just binary acids. You have a handful of polyatomics, some of which you are allowed to use the BI prefix on if you're using references from the lab book. And then 6 through 9, again, are kind of a mixed bag of various categories of nomenclature. There are 120 points. Okay, I know that sounds kind of both daunting and kind of like, oh my God, how am I going to get through it? Okay, we've been kind of doing it this way for quite a while. The idea is, and it literally sort of is a head pounding event. If you do 100 and some of these particular style of doing names or doing formulas, eventually your brain begins to develop connections that certain things, certain formulas tend to have certain styles to their names. And then going back in the other direction, certain names have to look certain ways when you write them out. So the idea is to develop the understanding, because these things don't go away, okay? Even though we focus a lot on naming them for chapter 2, a huge chunk of that information, especially in terms of charges, continues onward through the rest of the semester. So this is a one chunk at a time kind of thing. So sometime in the next week or so, you need to make sure you finish your separation of a mixture calculations. There's a pre-lab for separation of mixture, which is in your lab book. I'm hoping, fingers crossed, the bookstore got them in. I know that a couple people who ordered things actually managed to get them. I have a couple other people, I think, who don't have me for lecture that I'm still uncertain about as to whether or not they got a lab book. If it gets on into next week and you still don't have a lab book, definitely send me some email, okay, so that I can kind of keep up with where we're at. I'm hoping we get this all resolved. I'm utterly frustrated that the bookstore didn't order at least 50 to start with, because I mean, we're not changing the lab book. We have to notify them in advance when that sort of thing happens. So I'm not really sure why that ended up being such a kind of minor disaster. Questions about lab stuff? All right. Let us dig a little deeper into some chapter 3 information. And then we'll take a bit of a break and get a little bit closer to the end of chapter 3. All right, so the last chunk of information that we were dealing with on Tuesday involved the idea of empirical formulas versus molecular formulas. And we were looking at this molecule that we were told contained lead and chlorine, and you were given some information that allows you to calculate moles, which will then allow you to figure out what your ratio is. All right, moving onward to something with more than just 2 elements. So we have the next compound is an organic compound. It has carbon, hydrogen, nitrogen, and oxygen. And I gave you the masses of the elements for that particular sample. We're going to set it up very similarly to the one above. I'm going to take each of these masses and their element, and I'm going to hook it all together here and do my divisions. So my carbon, I am dividing by 12.01. That is my atomic mass for carbon. For my hydrogen, in part because hydrogen is so very small, I kept all of my decimal places. I kept the 1.008 when I did that one. For my nitrogen, I have 14.01, and I'm using the rounded version for my oxygen, which is 16. So looking horizontally across each line then, when I have done my division, I end up with moles. So for my carbon, I have 0.0249 moles. For my hydrogen, 0.058 moles. For my nitrogen, 0.017. And for my oxygen, 0.0083. All right, continuing across horizontally. Of those four elements, you must pick the smallest number of moles, which in this case happens to be the number of moles for oxygen, the 0.003. And now you are going to go back and divide each of your other mole amounts by that smallest number. When you do your division, a couple of them don't give you exactly a whole number. The first one does. 0.0249 divided by 0.0083 gives me 3. For my hydrogen, my division gave me 0.6 or 6.99, which I am going to round to the closest whole number, 7. For my nitrogen, again, a little bit of rounding. In this case, I'm rounding down very slightly from 2.05 down to 2. And because I am dividing by the one I picked, my oxygen comes out to be 1. So when you write your empirical formula, usually, unless a textbook or other problem is telling you to do it in a different order, usually you just spit back the information in the order in which it was given. So because I gave you carbon, then hydrogen, then nitrogen, then oxygen, that's how I reported back my empirical formula. I've got C3, H7, N2, and remember, you don't need to write the 1 for your oxygen. The 1 is implied. Now, there's another way that you might see the information presented to you. Sometimes instead of starting out with so many grams of this and so many grams of that, you may be given information in terms of percentages. Okay, think about what a percent means. Also, this harks back to this past week's lab as an idea for percentages. Percentages mean some number out of 100. So if you have 12% something, if your ammonium chloride was 12%, that means if you had a full 100-gram sample, 12 of those 100 grams would have been your ammonium chloride. I also kind of picked on iron again. If I had an iron ore sample, ore is usually not very pure. But if my iron ore was 18% iron, again, extrapolating this, every 100 grams of sample would have had 18 grams of actual iron. So if you've got sodium, silicon, and fluorine, and I actually know what the percentages are, I can do a similar type of calculation here. One of the things you will notice is that unlike the previous two examples that started out with grams, my numbers of moles are actually a little bigger. I have things that might come out to be more than just 1 mole. So my 24.5% sodium means that I can move my decimal, make it 24.5 grams, because I'm assuming I have 100 grams. When I divide by the atomic mass of sodium, 22.99, I don't get a teeny tiny number. I get a somewhat larger number. I get 1.07. For my silicon, I have 14.9%, which then becomes 14.9 grams. My silicon weighs 28.09. That gives me a little over half a mole. For my fluorine, 60.6% will give me 60.6 grams. Divide by 19. And again, going horizontally across the page, now that I have my moles, pick the smallest of them, in this case, the silicon. I'm going to divide each of my 3 mole amounts by the smallest one so that I get a ratio. My first division gives me 2.02, so I will round it down very slightly to 2. My silicon gives me the same number again, so 1. And for my fluorine, again, I'm going to do a little bit of rounding down. My math gave me 6.02, and I'm going to round that down to 6. Now, there's one thing additional in the world of doing empirical formulas that freshman chem deals with. If you go to higher levels of chemistry, there are deeper variations. We are going to look at the one that involves a situation where when you do your ratio, you can't round it. The ratio ends up halfway, and you have to do something a little bit different to finish out that problem. If we look at magnesium and nitrogen, I've got 0.71 grams of magnesium and 0.273 of my nitrogen. Problem starts out the same way. Divide by your atomic masses. I'm going to get 0.0292 for my moles of magnesium and 0.0195 for my nitrogen. Smaller one divided by I said that backwards. Larger one divided by smaller one gives me 1.5. I am not allowed to just simply round up to 2. You must multiply both of your values that were produced by the division step by 2. So 1.5 times 2 becomes 3. And then 1 times 2 gives you 2. And this gives you an empirical formula of Mg3N2. One of the things to kind of consider here is this is a way that you can get even and odd subscripts in the same molecule without trying to make judgment calls about rounding. So if you take higher levels of chemistry, you may run across, well, what if you had thirds or quarters or fifths? There are ways to fix those problems. We are only going to do ones that are fairly obviously whole numbers or pretty much dead in the middle with a half. We're not going to do the other version. So we're only going to consider kind of limited variations on this. All right, let us take about a 10-minute break, and then we will come back and add one more layer to this. All right, so let us return to a variation on doing empirical formulas. What if you knew your empirical formula and you had some information about its molecular weight / molar mass? How would you put those two pieces of information together? So I created a compound here that I know the empirical formula is 2 carbons, 1 hydrogen, and 4 fluorines. But I also have some information that its molecular weight is somewhere in the neighborhood of 200 grams per mole. So how do I put those pieces together? First thing I'm going to do is figure out, well, what if my empirical formula and my molecular formula happen to be the same thing? I need to know how much 1 unit's worth of my empirical formula would actually weigh. So back to periodic table information, I've got 2 carbons, so 2 times my 12, 1 hydrogen, 1.008, and 4 fluorines, 4 times 19. Add them all together, and that gives me an empirical weight of a little over 100. If I take my known approximation of my molecular weight and I divide my empirical weight, I get a number that's awfully close to 2, 1.98. I'm going to round it because it's super, super close to a whole number. And therefore, I can write my molecular formula 2 different ways, okay? If you go trolling through the internet for various examples to compare to, some of them will put parentheses around your empirical formula and then put a subscript on the outside edge. Some of them will go ahead and multiply it through, giving you C4H2F8. It doesn't really matter a lot about which way you express it. I'm aware that different sources will give you answers in slightly different methodology there. So we are also going to talk about hydrates. Okay, let me stop and grab my lab book here for a second. So in your lab book, part of the next week of cycle involves doing the lab that is known as percent water in a hydrated salt. We are going to be using crucibles with the Bunsen burners in order to heat the water away from your hydrated salt. So it starts on page 85 in your lab book. There is a pre-lab that you eventually need to do that looks like this on page, if you're looking at the big number there, it's 87. If you're looking at the little number, it's actually a 93. And then there is a report page, which you will need also. So keep that in mind as things for next week. But because all the labs, regardless of if you have me for lab or not, we all do the same labs. I want to spend a little time talking about the math calculations that are involved in this. All right, a hydrate starts out life as a salt, okay? A salt, not necessarily meaning table salt, just a salt, meaning an ionic compound. And it will have a number of water molecules that are loosely attached to it. The numbers tend to range between 1 and 10, but there do exist a few hydrates that have 11 or 12 water molecules attached to them. More typically, though, it tends to be a single digit. So if I look at this one, CuSO4.5H2O, we're going to use the same prefix system that we used for the nonmetals. We're going to use the penta to represent the 5. So copper sulfate, in this case, it's copper 2 sulfate because your SO4 has a -2 charge. Therefore, your copper must have a +2 charge. And then the pentahydrate to indicate that your molecule has 5 waters attached to it. So one of the things that's true about hydrates is you can actually dislodge or drive off the water molecules by heating it. We are going to use crucibles, which look kind of like a little porcelain egg cup. And they also have a lid, however. And you are going to use those in order to contain your sample while you are cooking them. You will often see color changes or texture changes when hydrates are heated. If we look at copper 2 sulfate pentahydrate, it has a kind of sky blue color to it. And once you cook it, the deep blue goes to a really pale blue, almost gray shade. So you get a color change there. You also get a texture change, okay? Copper sulfate is relatively large, fat, glossy crystals that have kind of like a shine to them. Once you cook it, it's gonna like kind of turn into a dry, crusty powder. Not super unlike the salt crystals from the separation of a mixture lab of this week. They're not really pretty to look at. It's this weird kind of crusty mess. Okay, that's sort of what happens to your hydrate. I'm going to pick on, for my example, Epsom salts. Okay, this is what you can buy in the drugstore if you sprain your ankle. Okay, it's also a laxative, and you can use it for some other like soaking purposes. It is based upon magnesium sulfate, but there are a certain number of water molecules attached to it. So I created some fake data here, and I kind of shortcut it a little bit. I only gave you 1 decimal place in the creation of my data here. But I wanted to show you how the math works. So my empty crucible weighs 30.5 grams. And actually, while I'm thinking about it, let me go grab a crucible so that you can actually see what they look like. Yes, I have crucibles in my house. I've between teaching my kids some chemistry and the fact that I have taught a lot of other homeschooler kids chemistry, I actually have a whole closet full of glassware. So this is what a crucible looks like. Okay, remember I said it looks kind of like a porcelain egg cup. Okay, you're going to have a lid that sits on the top. And again, this kind of bears some similarity to the separation of a mixture lab that we did this week, where we put the watch glass on the top of it to help contain the sample while we were cooking it. So the same thing is going to be true of the crucible, in that we want to put a lid on it so we don't lose parts of our sample. All right, so I hypothesized that my crucible weighed 30.5 grams. Then I put a sample in it. Now it weighs 35.6 grams. I subtracted 35.6 minus 30.5, and my sample of my hydrate weighed 5.1 grams. So I cooked it. In fact, you will be cooking it at least twice. Sometimes you have to cook them 3 times in order to get them to cooperate. And again, this is a little bit similar to the first step of this past week's lab. Your weight goes down. Did you find my lid?
No, I'm trying to.
Oh, okay.
Pull the gel pens out of there.
So your weight goes down. It goes down to 33.0. What is left in my crucible is referred to as the anhydrous salt. In Latin, an is a prefix that means without. So anhydrous means you have a salt that has no water molecules attached to it. You have cooked them all away. So take your 33.0, subtract the weight of your empty crucible, and that will give you a mass of 2.5 grams. I forgot to put my G there for my grams. Now the difference between the two, okay, basically I'll kind of do it over the side here, of where did my 2.6 come from? So if I do my original mass of 5.1 minus my 2.5, that gives me my 2.6 grams. Not the end of the calculation, because this is only based upon their masses. One of the things that we've been covering in this chapter is, for instance, the fact that a mole of water and a mole of another salt don't have the same molar mass. So I need to divide by my molar masses here. I've got 2.5 grams of my magnesium sulfate, and I am dividing by 120.376. So that's 1 magnesium, 1 sulfur, 4 oxygens. And I have 0.0207 moles. Water is a much smaller molecule. I have 18 grams per mole. Ah, my kid found my lid.
Not the lid to that specific one, but it's a lid.
No, it's the lid to this one.
Oh, okay. It looked too big.
It's supposed to be too big.
It was in this like wooden container.
Oh, okay. I found my lid. Okay, so this is your lid. Okay, this fits in your little crucible, and yes, it does hang over the sides. It actually does that on purpose, because when you cook it, you're going to be cooking it kind of like this. You're going to park it at an angle so that some of the steam can escape more easily. Okay, which, and I will tip you off here, sometimes leads to broken lids because people knock them off and they fall on the floor. And these are ceramic, hence they break kind of easily.
Don't crack them.
All right, back to my math. All right, my water molecules weigh 18 grams per mole. I had 2.6 grams. I actually have quite a lot more moles of water than I have of salt. big number over little number. So 0.144 divided by 0.0207 gives me something that's not quite a whole number, 6.956. I am going to, however, round it to the closest whole number in order to determine what the formula of my hydrate is. So 6.956, I'm going to round up to 7. I will warn you that when you actually do this in lab, it is possible that your data may not look so pretty. And you may have to make decisions about whether you're rounding up or rounding down because of the way your data comes out. So this is kind of a thing that might happen when we do this lab next week. So kind of iffy there. All right, we are going to switch gears a little bit. And I also realized that sometimes when I type things and then I save them to a particular format, it doesn't, the spacing is kind of weird. All right, let me see if I can fix this and make it look a little bit more normal. All right, that helped a little bit. So molarity is a concentration. It has capital letter M, and it is moles of solute per liters of solution. So in the top part of that, you're only paying attention to the thing you are dissolving. But the bottom part is the combination. How much space does everything combined occupy? If you have a 1 molar solution, you have 1 mole of an item that is dissolved in 1 liter of solution. And I have a couple of examples here for you. We have 17.4 grams of sodium hydroxide, and we're going to dissolve it in 600 mils of water. So 2-step process. First, I need to figure out how many moles of solute I have. My molar mass for sodium hydroxide is 40, 1 sodium, 1 oxygen, and 1 hydrogen. Do your division, 17.4 divided by 40, and that will give you 4.435. And again, I have weird issues with my underlining here. Now I have to do a second step, because now I have to accommodate the fact that I didn't actually dissolve it in 1 full liter. I dissolved it in less than 1 liter. Move your decimal points, because the information was provided in milliliters. I have 600 milliliters, therefore it is 0.6 liters. My final number then from my calculation is this solution is 0.725 molar. I gave you one additional example just to kind of make sure you had a couple of different examples here. How about copper sulfate, the thing that we're doing the hydrate on? This is the not hydrated or anhydrous version. I have 5 grams of copper sulfate. It has a molar mass of 159.61. So if I have 5 grams and I'm dissolving it in 120 mils, my first step there gives me 0.031 moles of copper sulfate. Again, move my decimal place. I have 0.120 liters. And I know that kind of looks like a number 1. I probably should have capitalized that so that it makes it look more apparent as being a liter. So 0.031 divided by 0.12 will give you 0.258 molar. All right, so the last thing I want to touch on is the backwards version. Okay, same idea. You're making a solution here, but you are doing it by knowing what your concentration is and also knowing how much you want to make. This is more along the lines of what I do or Mr. Wheaton or Dr. McHugh does when we are doing lab prep. So if I have 0.75 molar calcium chloride, okay, so move your decimal places for your liters. I'm going to have 0.250 liters, multiply it by the 0.75, and that will tell me how many moles I have, 0.1875, and then multiply by my molar mass. Calcium chloride has 1 calcium and 2 chlorines, so it has a molar mass of 110.98. So all of this involves putting together your solution and topping it up to the way a particular volumetric flask looks. I actually don't have a volumetric flask. I have flasks like we use in the lab for doing titrations, but I don't have any volumetric flasks here to show you. I will maybe see if I can find a picture later for that. All right, and I think that is where I'm going to end this part of chapter 3, because you have a lot of stuff that's happening this weekend, okay? You got to turn in your homework by midnight. I know that some people have already turned it in. You have a test this weekend. And then there are things that are due next week, especially because I know that some people, in having difficulty in getting lab books, have not turned some things in yet, so that's fine. We're just trying to get caught up. Questions about the test of this weekend?
Would you be able to review one more thing with me?
Yeah. What are you looking for?
So it's like question number 9 on the homework. Krypton has 3 isotopes.
Oh, weighted averages.
Yeah, the weighted averages.
All right. I have a periodic table here that has isotopes on it. Let me pick on. Let me see if I can coerce the whiteboard into kind of doing what I want it to. All right. So we're going to say that we have, let's see, for instance, iridium only has 2 isotopes. So let's see, if I do iridium, and it has 1 isotope that is 191. And then it has a second isotope that is a little bit heavier, and it is 193. All right, and then I need some additional data here. I can switch over to the text part. All right, so of the iridium, 37.3% of the iridium isotopes are the 191 version. And then down here, that makes my other isotope 62.7%. All right, so now we get into the math part. All right, let's see if I can create a box that it'll let me do a box for the math. All right. So I'm going to do 191. Okay. Times, and I need to move my decimal place. I'm going to do times 0.373 because it needs to stop being a percentage and turn into a decimal. So 191 times 0.373 will give me 71.242. Okay, and then I need to do my other isotope. If you have more than two isotopes, you just keep doing the same thing. Okay, so then this one is 193 times 0.627. Actually, I realized this was supposed to be a percent sign and not a, actually not a, let's see if I can erase my, oh, there are times when I really hate this whiteboard thing. 62.7% is what this actually supposed to say. All right, so back over here. All right, so I'm going to do 193 times 0.627, and that will give me 121.011. All right. So 2 isotopes. I did the multiply step. Now I'm going to add them together to get the weighted average, which will go down here on the bottom. So I'm going to add 71.242 and 121.011. And that will give me 192.253. So one of the things that you can kind of see is the isotope 193 is more popular. Okay, there's way more of it. So your answer is actually closer to 193 than it is to 191. As I said, if you have more isotopes, you just do the same thing that I did in the 2 isotopes here, and you add them together. Keep in mind, there is never a division step when you are doing weighted averages. You do the multiplication step, and then you add, and that's the end of it. There should also be an example of this in your textbook too, as well as the one that I put in the notes.
Okay, and so it will be the higher number that will be the answer, or will be the ones after you add it?
It's the number after you add it. So the 192
you
point whatever came after the decimal places.
Okay. All right, got it. Thank you.
Other questions related to test topics? Okay, so test this weekend. It shuts down at like 1 minute to midnight on Monday, so you got to be done. If you're going to do it on Monday, if you're actually going to put off until Monday to do it, make sure you start by 8 o'clock, okay, on Monday night, because it will go dark at midnight on Monday. And getting it to undo is really complicated. I usually use drop tests rather than try to undo it, because it does this thing where it deletes people's data, deletes people's grades for a while before. Yeah, it's complicated. All right, other questions? Otherwise, I will see some of you Monday night for lab.
What time would the test be available, at Friday or on Saturday?
It starts, I think, at 1 a.m. tomorrow morning.
Okay.
Is what I set it to open up. And then that gives you basically pretty much 23 hours worth of Friday. all day Saturday, all day Sunday,
Okay.
all but a couple of minutes of Monday. Because I know I have a bunch of people who are either military or healthcare science or healthcare
Yeah.
employees who sometimes work weekends. So that's why I tried to make sure it wasn't just a weekend test, to try to make sure that everybody has time to take it.
Yep. Awesome. Thank you so much.
Otherwise, I will see some of you on Monday.
Thank you.